series on differential equations for undergraduate students. Today's topic is higher order linear differential equations. But before going to the today's topic, we will first do the example for the last lecture which we had left in the last lecture. Just recall what we have done in the last lecture, the damp force oscillation or vibration. Here we were having that the system of mass spring system where the damping was present and the vibration or the oscillation was governed by a force. That was that the differential equation which we were dealing with, the second order differential equation, and for this system the governing equation was my double dash plus cy dash plus ky is equal to f naught times cos omega t. Do you remember that we have taken this force as an example, that is we are talking about this kind of force where the force is f naught cos omega t, that is the deriving force, and we want the system's response corresponding to this force. This is a non-homogeneous equation. So, associated homogeneous equation would be my double dash plus cy dash plus ky is equal to 0. The solution of this non-homogeneous system we do know is the general solution is of the form yh plus yp, where yh is the general solution of this corresponding homogeneous equation and yp is the particular solution of this non-homogeneous equation. This general solution is called the transient solution and this particular solution yp, this is called the steady state solution. So, we are saying is that this steady state, what the term steady state means is that is it would remain as such, and this term is also saying is the vibration or oscillation would go on. So, let us see all these things with the help of the example. So, do the example. We do have a body of mass 4 kg is hanging on the spring with spring constant as 3 Newton. A damper is attached to the system that will exert a force of 8 Newton when velocity is 1 meter per second. Further, an external force of 425 sin 2t is attached to the body. If initially the body is displaced by 16 meter downwards and given that this initial velocity at that time is 26 meter per second downwards, then we have to find the equilibrium position and find the displacement at any time t. So, this question is basically of a mass spring system where this we are having is a spring and which is attached with a mass and a damper. There is one external force is also there and initially it has been displaced by 16 meters downwards and that has generated a velocity of 26 meter per second downwards. So, let us see is that is what the system is. We are having this is spring which has a spring constant as 3. There is a mass of 4 kg which is attached to with this one. Moreover, a damper is also attached with this one. What this damper is doing? This is changing the motion, that is it is exerting a force of 8 Newton when the velocity is 1 meter per second. We have to develop the equation, differential equation for this system, and moreover in this system there is an external force is also governing this mass, that is external force of 425 sin 2t. This force is upwards. So, we do have that what will be the solution, because differential equation we are having is that damping is also there and the spring constant is also there. So, the equation would be my double dash plus cy dash plus ky is equal to RT since an external force is also there. Now, what we are being given? We are given that this external force or this input is 425 sin 2t, that is RT is 425 sin 2t. Then we are being given this constant k, spring constant, that is 3. Now, what is this damping constant C? We are being given that the damping force is 8 Newton when the velocity, that is y dash is 1 meter per second, that is we do have cy dash as 8. So, at y dash as 1, which gives me that the damping constant C to be 8, and moreover this mass we are being given is as 4 kg. So, what will be our equation? Now, our equation would be 4y double dash plus 8y dash plus 3y is equal to 425 sin 2t. Now, we have got the governing equation for this given system. What we have to find it out here, this y is actually the displacement at any time t. So, we have to find out the displacement at any time t, that is the solution of this equation, which is y. Moreover, we have to find out when this system reaches to the equilibrium, that is when it is reaching to the equilibrium position, that is just giving the response to the initial force, that is this force. So, let us see that is how we are going to solve. So, we are going to solve this differential equation. Now, this is a second order linear differential equation with the constant coefficients, and the right hand side is not 0, that is it is non-homogeneous. We do know that for solving this equation we require first to solve the associated homogeneous equation. What will be associated homogeneous equation? That is the right hand side is 0, the equation is same, 4y double dash plus 8y dash plus 3y is equal to 0. Now, for solving this homogeneous equation we do know we require the characteristic equation of this one. What will be the characteristic equation? From here it should be 4 lambda square plus 8 lambda plus 3 is equal to 0. For finding the roots of this equation we will first factorize it. So, factorization gives me 2 lambda plus 1 into 2 lambda plus 3. Now, equate it to 0, we will get the two roots, one is minus half and another is minus 3 by 2 from here. So, we are getting two real roots which are distinct. So, what will be the linear independent solutions, two linear independent solutions corresponding to these two roots? As we do know, they should be e to the power minus t by 2 and e to the power minus 3 by 2. So, the general solution for this homogeneous equation would be C1 e to the power minus t by 2 plus C2 e to the power minus 3t by 2. Now, for finding out the particular solution for this non-homogeneous one, since we have this linear differential equation with the constant coefficient and this right hand side is of a special form, we can use the method of undetermined coefficient. So, based on this kind of thing we just go to the table which says is that if my right hand side is of the form k sin omega x, then I should choose my yp as a sin omega x plus b cos omega x. So, let us move to the solution. We do have this right hand side as 425 sin 2t. So, according to the table my RT is since 425 sin 2t. So, I should choose yp as a cos 2t plus b sin 2t. Now, here this a and b are the constant which we have to determine for this, but this equation which gives, that is so that this yp becomes a particular solution of this equation. For this what I have to do? I have to find out yp dash and yp double dash and substitute it over in this equation. So, yp dash would be minus 2a sin 2t plus 2b cos 2t. What will be yp double dash? Again differentiate, minus 4a cos 2t minus 4b sin 2t. Now, substitute this yp dash and yp double dash in this given equation. So, this substitution will give me, after all this clarifications, we get it, that is 16b minus 13a cos 2t minus 16a plus 13b sin 2t is equal to 425 sin 2t. Now, to find out this a and b, we will equate the coefficient of cos 2t and sin 2t on both the sides. So, on the left side we see the coefficient of cos 2t is 16b minus 13a. On the right hand side there is no term involving cos 2t, that is the coefficient is 0. So, we get the first equation as 16b minus 13a plus is equal to 0. Now, the coefficient of sin 2t on the left side is minus of 16a plus 13b and the right side is 425. So, we get the second equation as 16a plus 13b is equal to minus 425. Now, we are getting two equations in two unknowns. These are simple algebraic equations. We can get the unique solution, and that solution is actually a as minus 16 and b as minus 13. So, what will be our particular solution? Yp would be minus 16 cos 2t minus 13 sin 2t. So, what will be the general solution for this non-homogeneous equation? That would be as yh plus yp. Now, yh we do remember that we have got c1 e to the power minus t by 2 plus c2 e to the power minus 3t by 2 and plus this yp, that is minus 16 cos 2t minus 13 sin 2t. So, this is the general solution of this non-homogeneous system. Now, we are being given the conditions, initial ones, that the system has been put to the movement by displacing initially the object by 16 meter downwards and generating a velocity of 26 meter per second downwards. So, we have to get the particular solution. For that, the initial conditions, y0 is 16 because it is downwards, so the sign is plus. Similarly, the velocity, that is y dash at 0, that is 26 meter per second downwards, that is again the sign is plus. So, we have got y0 at 16 and y dash at 0 as 26. Now, what was our general solution? Our general solution was this one. So, we find out first what will be y dash t. Y dash t would be minus half c1 e to the power minus t by 2 minus 3 by 2 c2 e to the power minus 3 by 2 plus 32 sin 2t minus 26 cos 2t. Now, initial condition means that is y at 0. When I put t is equal to 0, here I will get c1, here I will get c2 and here I will get minus 16, this part would be 0. So, we would get y at 0 is c1 plus c2 minus 16, this is given as equal to 16. So, the first equation we have got c1 plus c2 is equal to 32. Now, second initial condition is about y dash at 0. So, when I put t is equal to 0 in this y dash t, what I will get minus half c1 minus 3 by 2 c2, this term would be 0 and minus 26, that is minus half c1 minus 3 by 2 c2 minus 26, this is given to be equal to 26. So, we will get the second equation as c1 plus 3 c2 is equal to minus 104. Now, we have got two equations in two unknowns, we will solve it and we get from here that c1 as 100 and c2 as minus 68. So, what is our particular solution for the given system? That is y t is equal to 100 e to the power minus t by 2 minus 68 e to the power minus 3 t by 2 minus 16 cos 2 t minus 13 sin 2 t. Now, we are being asked two questions. The question one was that is what is the when it reaches to equilibrium position, and second was that is what is the displacement at any time t. Displacement at any time t, that is y t. So, we are getting is that by this function we are giving the displacement at any time t. Now, when it is reaching to the steady state solution, that is the equilibrium. Equilibrium means is it is reaching to the steady state solution, this solution and this part is 0. Let us see these things by the graphs. So, we see that this graph we do have this red line is actually the general solution, that is 100 e to the power minus t by 2 minus 68 e to the power minus 3 t by 2 minus 16 cos 2 t minus 13 2 t, and while this green line, this representing the particular solution that we had obtained as y h plus y p, that is minus 16 cos 2 t minus 13 sin 2 t. Now, we see this solution, that is solution of this problem. We do have that initially it is displaced by 16 meter downwards, that is the positive side. It is generating a velocity of 26 meter per second, that is the slope here is 26 meter or 26 with positive direction. So, this movement is, that is the displacement is on the positive side more higher, then it is coming down, but because it is a spring, it is coming down to something is near 0 or other going little bit negative, then it is again going up and then coming down and so on it goes on. We see after some time this red line and this green line, they are matching ones. This we called, if you do remember, the general solution as the transient solution, and this yp, that is the particular solution, as the steady state solution. So, this is the graph where we are saying is that this is the displacement or this will be the motion of that system, which after some times you are seeing is that it is matching towards the green line. If you see is that is exactly it is started matching after this at say 10 seconds, after this 10 seconds it is exactly matching with the green and red, that is we are not able to see finally that is where is the green and where is the red. So, we find out that is after that the system has stabilized. Now, the movement is not because of that initial pull or initial velocity. Now, it is only the response of the function deriving force, that is 425 sin 2t. So, we are reaching to the steady state solution after say 10 seconds. So, this is what the solution of you could say the displacement at any time t, that is been given by this red graph. When it is reaching to the steady state solution or equilibrium, that is at 10 seconds, after 10 seconds it is reaching. So, this is what we had concluded with this vibration one, that is it will move on like this oscillation will go on, that is why we are calling it vibration. It is going with equal ones, and like that one it will go on because of that input deriving force 425 sin 2t. Now, we will move towards today's topic, that is higher order linear differential equations. Now, we will move on from the second order to any arbitrary order n equation. So, what will be a differential equation of any order n? That should be a function of x, y dash, y n is equal to 0, where this y n we are saying is representing the nth derivative of y with respect to x. This equation would be called linear if this is of the form y n plus p n minus 1 x y to the power n n minus 1th derivative of y n minus 1 plus and so on, p 1 x y dash plus p naught x y is equal to r x. This is equation is of order n. We see the highest derivative which is occurring in this equation, that is of nth order. So, the order of this equation is n. The coefficients of yn minus 1, y dash, y, all these are functions of x only, that is p naught x, p 1 x, p n minus 1 x and r x, all these are the function of x only. So, this equation is linear since none of the terms y or y dash or its derivatives are coming in the same term simultaneously. So, it is a linear one. Now, if this right hand side is identically 0, the equation will be of the form y n plus p n minus 1 x, y n minus 1 plus so on, p 1 x, y dash plus p naught x, y is equal to 0. This would be called the homogeneous linear equation of order n. When this is not 0, then we call it non-homogeneous linear equation of order n. This we are calling as a standard form, since the coefficient of y to the power n, the coefficient of the nth derivative y n is 1. This could be any p n x, but that to make it as of order n, we require that p n x must not be 0 function. So, we can have this p n x as 1. So, this we are calling a standard form. Now, let us revisit some definitions in the differential equation. So, first is solution. What will be the solution of nth order differential equation? As usual, we have done that the solution should be any function which is satisfying the equation. So, what is special about this one? A solution of nth order differential equation on some open interval I is the function y x, which is differentiable n times on I, and the function and its derivative satisfy the equation. So, the function and its derivative satisfy the equation that fulfill the condition of solution. What I require that this function would be solution only if it is n times differentiable. So, that is the difference between the whatever the definitions we have done earlier. Now, we will concentrate first on the homogeneous equations. We have seen in the second order homogeneous equations that we have got one fundamental theorem which said is that is linear combination of solution is also the solution. Similarly, here also we do have superposition principle or the linearity principle. What this says? This says for homogeneous linear differential equation y n plus p n minus 1 x y n minus 1 and so on plus p 1 x y dash plus p naught x y is equal to 0. The sum and the constant multiples of the solutions on some open interval I are again the solution of this equation. In other words, the linear combination of the solution of the homogeneous linear equation are also solution of the same equation. That is, if suppose I do have y1 and y2 as the two solution for this homogeneous linear equation. Then C1 y1 plus C2 y2 will again be a solution of this homogeneous linear equation of order n. Let us just see some more terms over here, that basis, general solution and particular solution. First the general solution. For in a third linear differential equation which is homogeneous of this form, that is standard form y n plus p n minus 1 x y n minus 1 plus so on plus p 1 x y dash plus p naught x y is equal to 0, the general solution will be of the form C 1 y 1 plus C 2 y 2 plus C n y n, where this y 1 y 2 y n they are linearly independent solution of this equation, and the C 1 C 2 C n are the arbitrary constants. Now, these linearly independent solutions of this equation they are called basis or fundamental system of solutions. Moreover, what we do have here is, since this is an nth order equation, this will actually have n linearly independent solutions, and those n linearly independent solutions will form the basis or the fundamental system of the solution, and the general solution of this equation will consist of the linear combination of all these linearly independent solutions, where the C 1 C 2 C n would be arbitrary constants, and this general solution will include all the solutions. Moreover, a particular solution would be what? When I do give the specific values to this constant C 1 C 2 C n, that solution would be called a particular solution, that can be obtained by given certain conditions. We say that it is satisfying certain conditions, so that I could find out the values of this C 1 C 2 C n. Now, let us do some examples to understand the concepts just now we had learned. Of course, we have done it in the second order and the first order, but we will again redo for the nth order, just generalize it. First example is the function x, 3x, x square are linearly dependent on interval I. That is, first we are trying to understand the linear dependence and independence. We have already done the linear dependence and independence in the terms of two solutions. Now, we are moving to the higher one. So, first thing is, that is what we would call linear dependence or independence. C 1 y 1 plus C 2 y 2 plus C n y n, this is called a linear combination, where y 1 y 2 y n are the functions and the C 1 C 2 C n are constant. This is called a linear combination. Now, if this linear combination is identically equal to 0 for some constant C 1 C 2 C n, where all these C 1 C 2 C n are not 0, that is for some non-zero constants, then we call that y 1 y 2 y n are linearly dependent. So, what we have learned, that from linear combination, if it is identically 0 for some non-zero constant, then the functions y 1 y 2 y n would be linearly dependent. Now, in this question what has been asked, that is show that they are linearly dependent on any interval. Let us choose here C 1 as 3, C 2 as minus 1 and C 3 as 0. So, now I have chosen two constants which are non-zero and one zero constant. Since there are three functions, I have chosen these three constants. Now, let us see what would be C 1 y 1 plus C 2 y 2 plus C 3 y 3. This would be actually 3 times x minus 3 times x, which is equal to 0 for all x, whatever be the interval I. That says is that linear combination is 0 with non-zero constants. The non-zero constants we had 3 and minus 1. Thus, what we conclude, that y 1, y 2, y 3 are linearly dependent. Now, let us revisit the definition of independence also. As we said is, that is, in general solution we require n linearly independent solutions. So, what we would call linear independence. So, for the n functions, again we will use with the linear combination. The n functions y 1, y 2, y n are linearly independent if there does not exist any non-zero constant such that the linear combination C 1 y 1 plus C 2 y 2 plus C n y n is 0. That says is that this linear combination would be 0 if and only if the C1, C2, Cn are all 0. That is, in other words, we say the linear combination is 0 if and only if all C1, C2, Cn are 0, then we call that y1, y2, yn are linearly independent. We had also learned this linear dependence and independence, if you do remember, in second order equations using something called the Wronski determinant or Wronskian. That is, again we can see that Wronskian in the form of n functions or n solutions. So, let us do the definition of dependence and independence in the form of Wronskian. What will be the Wronskian of n functions? That we define as, for n functions y1, y2, yn, the Wronskian wy1, y2, yn is being defined as the determinant where the first row is containing all the functions y1, y2 and yn. The second row will contain the derivative of y1 dash, that is y2 dash and yn dash, and so on. The nth row will contain the n minus first derivative of the function y1, y2, yn. So, the Wronskian for the n function would be a determinant of order n containing these functions and their derivatives. We would say that when the functions will be linearly dependent and independent, if this Wronskian, that is this determinant, is not 0 for any x, we call that y1, y2, yn are linearly independent. If this determinant is 0 for some x, we call that their functions are linearly dependent. So, now let us just use this definition in our own example. We had the example that we had the functions x, 3x and x square. What is the Wronskian of these functions? Of course, that should be first row will contain the functions x, 3x, x square, second row the first derivative, its derivative is 1, its derivative is 3 and its derivative is 2x. Now, the second row, the second derivative of the function are the again the derivative of the last row. So, the derivative of 1 is 0, 3 is 0 and 2x is 2. Now, if I find out the value of this determinant, I would just like to expand it with respect to the third row. So, with respect to this 2, we would be getting is the determinant of order second x and 3x and 1 and 3. So, what we will get 3x minus 3x, that is 2 times 3x minus 3x, which is 0 for all x. That again gives me, that is my Wronskian has come out to be 0 for all x. So, y1, y2, y3 they are linearly dependent. Now, let us do one more example to learn about the solution. Find the solution of y4 minus 5y dash plus 4y is equal to 0. y4 means the fourth derivative of the function y. Now, we see this is a linear differential equation where the coefficients are 4, 5 and 1, that is they are constants. Now, we will just try with the similar conditions which we have done in the first order and second order when we had the constant coefficients. We tried with the solutions of the kind e to the power lambda x. So, here again we will move to that form of solution, that is, let us say e to the power lambda x is a solution. If this is a solution, then this function and its derivatives y dash, y double dash and so on, they must satisfy this equation. So, let us try. What will be y dash? Lambda times e to the power lambda x, y double dash lambda square times e to the power lambda x, the third derivative lambda cube times e to the power lambda x, and the fourth derivative would be lambda to the power 4 e to the power lambda x. Now, I substitute, if this is a solution, I will substitute this and will try to satisfy the equation. So, if I am substituting in this equation, I would get lambda to the power 4 e to the power lambda x minus 5 lambda square e to the power lambda x plus 4 e to the power lambda x is equal to 0. Now, rewriting it, we get lambda to the power 4 minus 5 lambda square plus 4 into e to the power lambda x is equal to 0. Now, if e to the power this y is a solution, this must be true. This will be true only if either e to the power lambda x is 0 or this coefficient that lambda to the power 4 minus 5 lambda square plus 4 is 0. Now, this e to the power lambda x, this cannot be 0 because we are taking this as a solution. So, it should not be a trivial solution, that it should not be 0 for all x. That says is that my lambda to the power 4 minus 5 lambda square plus 4 should be 0. This if you do see is that is this similar to that what we are getting is characteristic equation in second order. So, this also we call the characteristic equation. Now, this is a fourth order one. Let us factorize this equation. What this factorization would give me? Lambda to the power 4 minus 4 lambda square minus lambda square plus 4. Now, you see if I take common from here lambda square and here from minus 1, we would get lambda square into lambda square minus 4 minus lambda square minus 4 is equal to 0, which gives me lambda square minus 1 into lambda square minus 4 is equal to 0. That says is further factorization lambda minus 1 into lambda plus 1 lambda minus 2 into lambda plus 2 is equal to 0. So, we have got the roots of this equation as 1, minus 1, 2 and minus 2. So, the roots are 1, minus 1, 2 and minus 2. Now, what we have seen? We have got the fourth order equation. The characteristic equation was of the order 4. So, we got the degree 4. So, we have got the 4 roots. Now, all these roots are now we are seeing is they are distinct and real. So, let us say that is we will get the 4 solutions, say the solutions we would say corresponding to the 1 e to the power x, corresponding to the minus 1 e to the power minus x, corresponding to 2 e to the power 2 x and corresponding to the minus 2 e to the power minus 2 x. Now, these solutions will form a basis only if they are linearly independent. So, for checking linear independence, let us use the WORNSKIAN. So, WORNSKIAN we are having that is it is the 4 solutions. So, we will have the determinant of order 4, where the first row of course as usual we would have all the solutions e to the power x, e to the power minus x, e to the power 2 x, e to the power minus 2 x. Second row the derivatives. So, e to the power x minus e to the power minus x, here 2 times e to the power 2 x, this one would be minus 2 times e to the power minus 2 x. Third row again the second derivative or the derivative of the previous row. So, like this one, and the last row would be the derivative of the previous row. So, again we are having e to the power x minus e to the power minus x 8 times e to the power 2 x and minus 8 times e to the power minus 2 x. Now, to solve this determinant we can take common from the first column e to the power x, from the second column we will get e to the power minus x, the third column we would get e to the power 2 x and the fourth column we would get e to the power minus 2 x. So, this multiplication of all these we would get as 1, and what will be remaining here is in the first column 1, second column 1 minus 1, 1 minus 1, the third column we will get 1, 2, 4, 8 and in the fourth column we will get 1 minus 2, 4 minus 8. Now, if we just solve this determinant we will get the value of this as 144, which is not 0. That says is that all my these solutions which we had formed out they are linearly independent. So, what will be the basis for the system? That is basis are the fundamental system for of this solutions, that would be y1 is e to the power x, y2 as e to the power minus x, y3 as e to the power 2 x and y4 as e to the power minus 2 x. So, the general solution for the given differential equation would be c1 e to the power x plus c2 e to the power minus x plus c3 e to the power 2 x plus c4 e to the power minus 2 x. So, we have got the general solution for this differential equations. Now, we will move to the next term, initial value problem. What is the initial value problem? The initial value problem will contain the differential equation, that is nth order differential equation, homogeneous one, and n initial condition. Since this is nth order differential equation, we will have now n initial condition. We had seen that first order equation we had got only single initial condition. In the second order equation we have got 2 initial conditions. Now, we will have n initial conditions. What are those n initial conditions? They would be y at some point x naught is k naught, y dash at some point x naught is k 1 and so on. The n minus 1th derivative at x naught is k n minus 1. So, this would be called initial value problem. They would give me the actually the particular values for the constant C1, C2, Cn, that is arbitrary constant in the general solution. Now, existence and uniqueness theorem for initial value problem. What we say is that if p naught x, p1 x and pn minus 1 x are continuous functions on some open interval I and x naught belongs to I, then the initial value problem which is containing this nth order equation y n p n minus 1 x y n minus 1 plus p 1 x y dash plus p dot x y is equal to 0, and in initial conditions y at x naught is equal to k naught, y dash at x naught is equal to k 1 and y n minus 1 x at x naught is k n minus 1. This will have a unique solution on the interval I. That is, I would get a single values, the unique values for C1, C2, Cn in the general solution. Existence of general solution. Result says, if the coefficients p naught x, p 1 x and p n minus 1 x in this linear differential equation which is homogeneous y n p n minus 1 x, y n minus 1 and so on, they are continuous on some interval I, then every solution y x of this equation will be of the form C 1 y 1 plus C 2 y 2 plus C n y n, where this y 1 y 2 y n are the basis of the solutions and C 1 C 2 C n are arbitrary constants. That is, this nth order equation will contain or will have n linearly independent solutions, and the general solution would be a linear combination of those linearly independent solutions. Moreover, all the solution of this equation would be included in the general solution. That is, there would be no singular solution for this differential equation of linear differential equation of order n, which is homogeneous. So, let us come first with the higher order homogeneous linear equation with constant coefficients. What nth order homogeneous linear equation which is of the form y n plus a n minus 1 y to the power y n minus 1 plus so on a 1 y dash plus a naught y is equal to 0, where these coefficients a n minus 1, a n minus 2, a 1, a naught, they are all constants. So, now they are not the function of x, they are just the constants, then we call this nth order homogeneous linear equation with constant coefficients. Now, we do have done the solution of these kind of equations in the first order and second order. There we had used the function of the form e to the power lambda x as the solution. So, here also we will find out the method to solve this equation. We will use again this kind of function as a solution. That says is that we are having y dash as lambda to the times e to the power lambda x, y double dash as lambda square e to the power lambda x and so on. The nth derivative would be lambda to the power n times e to the power lambda x. If this function is a solution of this one, then we would get that this function and these derivatives must satisfy this equation. So, if I substitute this here in this equation, we would get lambda n e to the power lambda x plus a n minus 1 times lambda to the power n minus 1 into e to the power lambda x and so on, a naught e to the power lambda x is equal to 0. Rewriting this, I would get one equation as lambda n to the power n plus a n minus 1 times lambda to the power n minus 1 and so on, plus a 1 lambda plus a naught into e to the power lambda x is equal to 0. Since we have started that e to the power lambda x is a solution, so it can't be 0. So, if e to the power lambda x is a solution, that must satisfy this equation, and this equation will be satisfied if either this part is 0 or this part is 0. This part can't be 0. So, we will get that this part is 0, which we are calling the characteristic equation. So, the characteristic equation we are getting lambda to the power n plus a n minus 1 lambda to the power n minus 1 and so on plus a 1 lambda plus a naught is equal to 0. Now, we see this is equation of degree n. Till now we have done the second order equation, where we have got the characteristic equation as having say a quadratic equation. Just now we had finished one example where we had used a fourth order equation, and the characteristic equation we have got of degree 4, and that equation was having 4 roots. So, this equation will have n roots. That says is, now if you do remember in the second order equation, we have got the 3 cases, that is their real roots, double roots and then complex roots. Now, since they are n roots, so we will have many more cases. What will be those kind of roots? Let us see. They would be either real roots or the complex roots. then the real roots also could be either simple roots, that is they are not repeated one, or the multiple roots, that is they are repeated one. Similarly, in the complex roots also we can have the simple roots, that would be a conjugate pair, or that conjugate pair is being repeated many times, that is the multiple roots. That is, in all we have got 4 cases: simple real roots, simple complex roots, multiple real roots and multiple complex roots. Let us see one by one all these 4 cases and what will be n linearly independent solutions in all these 4 cases. So, the case 1, simple real roots, that says if the characteristic equation lambda n plus a n minus 1 lambda to the power n minus 1 and so on plus a 1 lambda plus a naught is equal to 0, this is having n roots lambda 1, lambda 2, lambda n, they are all real and distinct. Then we would say n linearly independent solution should be e to the power lambda 1 x, e to the power lambda 2 x and so on e to the power lambda n x. These solutions would be linearly independent. If they are linearly independent, then we will get the general solution as C 1 e to the power lambda 1 x plus C 2 e to the power lambda 2 x plus C n e to the power lambda n x. Now, we said is if they are linearly independent. Now, let us just check whether they are linearly independent or not. We will again use the WORNSKIAN. So, WORNSKIAN for this would be nth order determinant, where the first row will contain all the solutions e to the power lambda 1 x, e to the power lambda 2 x and so on e to the power lambda n x. Second row will have the first derivative and so on. The nth row will have n minus 1th derivative of these functions. So, now if I again go to solve this determinant, we will find it out that from the first column I can take common e to the power lambda 1 x, second column e to the power lambda 2 x and so on the last column e to the power lambda n x, that is e to the power lambda 1 plus lambda 2 plus lambda n plus lambda n x, and the determinant we will get 1 1 1 the first row, second row lambda 1 lambda 2 lambda n, the third row lambda 1 is square lambda 2 is square lambda n is square and so on. The last row we would have lambda 1 to the power n minus 1, lambda to the power n minus 1 and so on lambda n to the power n minus 1. This is a special kind of determinant, this is not 0. We can check it by just that is by doing all those row operations and column operations for finding it out. Actually, the value of this determinant is turns out to be all this term e to the power lambda 1 plus lambda 2 and so on here minus 1 to the power n into n plus n minus 1 by 2 into v, where v is actually the product of lambda I minus lambda j for all I less than j. Now, since we are having this all my roots lambda 1, lambda 2, lambda n are distinct, that is lambda I minus lambda j will not be 0 for all I less than j. When I is not equal to j, they will not be 0. That says is this product of non-zero real numbers, this will never be 0 and that gives that this determinant will not be 0. So, WORNSKIAN is not 0, that says my solutions e to the power lambda 1 x, e to the power lambda 2 x, they are linearly independent. Now, let us come to the second case, that is simple complex root. We do know that is whenever the complex roots are occurring, they would occur in the pairs. So, if my characteristic equation has a complex root, they will always occur in conjugate pair, that is if the one root is of the form alpha plus I beta, I must have the second root of the form alpha minus I beta. Now, suppose this is simple, that is it is occurring only once. So, corresponding to this lambda 1 and lambda 2, these two roots, we will have two linearly independent solutions as e to the power alpha x cos beta x and e to the power alpha x sin beta x. They are linearly independent of each other. Moreover, if I am having all other roots, they are simple real roots or they are different simple complex roots, they will also be linearly independent to them. These things we will learn in the examples. Now, come to the case 3, that is multiple real roots. What it says, if my characteristic equation lambda to the power n plus a n minus 1, lambda to the power n minus 1 and so on plus a 1 lambda plus a naught is equal to 0, this has real roots, all the roots are real, but all the roots are not distinct. Say some root lambda star is repeated k times, that is I do have something lambda minus lambda star to the power k, that we are calling multiplicity k. Then one solution would be of course e to the power lambda star, but what will be about the other solution? So, we require actually k linearly independent solution. Those k linearly independent solution with respect to this lambda star would be actually this. You see, first solution of course as e to the power lambda star x, then the second solution will have x times e to the power lambda star x and so on. The kth solution we will have x to the power k minus 1 e to the power lambda star x. How we had obtained? If you do remember, we have done the double real root in the case of second order equation, and there the second solution we had obtained by the method of variation of parameter, or that by substituting the solution. So, with the same method we are finding out these k linearly independent solution with respect to this root lambda star which is being repeated k times. Now, let us come to this when this we do have case 4 multiple complex roots. Multiple complex roots, that means it is not only the single root, the complete pair would have been repeated. So, if this characteristic equation thus has a complex conjugate pair, that is alpha plus I beta and alpha minus I beta, and this is being repeated k times, that is this complete pair is having multiplicity k. That says now we require 2 k linearly independent solutions. So, what will be those 2 k linearly independent solution? Let us see, that is how we are obtaining this 2 k linearly independent solution. One we will obtain with respect to, if you do remember, if they would have been simple one, we would have e to the power alpha x into cos beta and e to the power alpha x sin beta. So, we will have first e to the power alpha x cos beta, that is the one solution. The other solution with the multiplicity k, that is k, we would have x times e to the power alpha x cos beta x and so on, x to the power k minus 1 e to the power alpha x cos beta x. Similarly, the k plus first solution we will go with this e to the power alpha x sin beta x, and again we will have the k solution, that is k plus 2 as x times e to the power alpha x sin beta x and so on. 2 kth solution would be x to the power k minus 1 e to the power alpha x sin beta x. So, we are having the roots that solutions, one corresponding to the e to the power alpha x cos beta x, there we would multiply x square and so on till x k power k minus 1, and in the second solutions we do have is that is e to the power alpha x sin beta x, then multiply x square and so on till x to the power k minus 1. That is what we had learned. In each case we will get n linearly independent solution whatever be the situation, and those solutions let us say they are y1, y2, yn. So, the general solution will always be of the form c1 y1 plus c2 y2 plus cn yn. Now, let us do some example to understand these things. Let us do the first example. Solve y4 minus 16y is equal to 0. What is the solution? So, this is a linear differential equation of order 4 and it is homogeneous. So, first we would find out the characteristic equation. The characteristic equation, if you do see, we have got is lambda to the power n plus a n minus 1 lambda to the power n minus 1 and so on. So, here what we will get, lambda to the power 4 minus 16 is equal to 0. Now, factorize this one, what we will get, lambda minus 2 lambda plus 2 into lambda square plus 4 is equal to 0. Thus, what we will get the roots? We will get the roots as 2 minus 2 and minus 2y and plus 2y. So, what we are getting, actually we are getting 4 roots where the 2 roots are real and they are distinct, the 2 roots are the complex conjugate. And in the complex roots we are having is that the term alpha plus I beta and alpha minus I beta I am having is that alpha part is 0 and we are having the beta as 2. So, what will be corresponding? 4 linearly independent solution. With respect to these real roots we would have, because they are distinct, e to the power minus 2x, with 2 we would have e to the power 2x. Now, with this complex conjugate ones we would have cos 2x and sin 2x. Now, all these 4 roots are are these 4 solutions are linearly independent. As I said is that is we have find out these 2 linearly independent, these 2 linearly independent, we had already claimed it. Now, we want to check that is all these 4 are linearly independent. Let us again move to the method of WORNSKIAN, that is first find out the WORNSKIAN of this one. So, the general solution would be of course, if they are linearly independent, this would be of the form C1 e to the power minus 2x plus C2 e to the power 2x plus C3 cos 2x plus C4 sin 2x. Let us check about the linear independence. What will be the WORNSKIAN? Because it is a 4 solution, so it will be of order 4 determinant, where the first row would have all the solutions e to the power minus 2x, e to the power 2x, cos 2x and sin 2x. Second row we will have the derivatives. So, as usual the derivatives, then the third row derivative of the second row, and the fourth row the derivative of the third row. So, we have got this determinant. Now, again we will take e to the power minus 2x common from the first column, e to the power 2x from the second column, and from here we will get cos 2x and sin 2x. So, what we are getting is that is it would be actually 124 times cos 2x sin 2x. This will be not exactly cos 2x sin 2x, this would be a function of this one. So, this will not be 0 for any x. That says is that we are getting the 4 linearly independent solutions. So, come to the second example. Solve the initial value problem y triple dash minus y double dash minus y dash plus y is equal to 0 with initial conditions y at 0 is 2, y dash at 0 is 1 and y double dash at 0 is 0. Now, so the equation is homogeneous linear differential equation of order 3 with the 3 initial conditions. So, for solving it we first get the characteristic equation as usual lambda cube minus lambda square minus lambda plus 1 is equal to 0. We see that with the factorization that it is nothing but lambda square. If I take common from here and here from minus 1, I would get lambda minus 1 and lambda minus 1, that is we would get lambda square minus 1 into lambda minus 1, which is same as lambda minus 1 into lambda plus 1 and lambda minus 1. So, lambda minus 1 whole square into lambda plus 1. If I equate it to 0, I will get the 3 roots where the root 1 is repeated 2 times, because I am having lambda minus 1 whole square and lambda plus 1 give me the root minus 1. So, I get the roots minus 1, 1 and 1. So, I have one root which is repeated 2 times. What will be the 3 linearly independent solution? The solution corresponding to the first root would have e to the power minus x, with the second root I would have e to the power x. Now, the third root is repeated one. So, we will go with the method, that is we multiply x with this one and the third solution would be x times e to the power x. These 3 are linearly independent solutions. So, the general solution will be of the form C1 e to the power minus x plus C2 e to the power x plus C3 x times e to the power x. Again we can check that these 3 are linearly independent with the help of WORNSKIAN. So, WORNSKIAN here would be e to the power minus x, e to the power x, x times e to the power x. So, if we take the derivatives and the second derivatives, now if I take the common e to the power minus x, e to the power x and e to the power x, I would left with e to the power x and the determinant as of the form 1 1 x minus 1 1 x plus 1 and 1 1 x plus 2. If we solve it, we do get it is equal to 4 times e to the power x, which is not 0. That says is that these 3 solutions are linearly independent. Now, we have to solve the initial value problem, that is we have to find out the particular solution. The given initial conditions are y at 0 is 2, y dash at 0 is 1 and y double dash at 0 is 0. Our general solution was C1 e to the power minus x plus C2 e to the power x plus C3 x times e to the power x. What will be y dash? That would be minus C1 e to the power minus x plus C2 e to the power x plus C3 x e to the power x plus C3 e to the power x, and double dash, that is second derivative, would be C1 e to the power minus x plus C2 e to the power x plus C3 x times e to the power x plus 2 twice C3 e to the power x, that is 1 from C3 e to the power x as here and here. Now, put the initial conditions, that is put y x at 0 here. So, y at 0 I will get C1 plus C2 which is given is equal to 2. From the second one, if I am putting x is equal to 0, this will give me minus C1 plus C2 plus C3, this is equal to 1, this is given, and the third condition gives me C1 plus C2 plus 2 C3 is equal to 0 from here. So, I am getting 3 equations in 3 unknowns, and we can solve it, we can get the unique solution. That solution we are getting as 0, C1 as 0, C2 as 2 and C3 as minus 1. So, what will be the solution of our initial value problem? That will be 2 times e to the power x minus x times e to the power x, that is C1 is 0, C2 is 2 and C1 is minus 3. So, finally, what we are getting is 2 minus x times e to the power x. We can check that this is solution for the given differential equation. Moreover, this solution is satisfying all these initial conditions. So, this is the solution of initial value problem. So, today we had learned about higher order homogeneous linear equations with constant coefficients. We had learned how to solve them, we had learned certain definitions in the terms of higher order one, and we had learned homogeneous one, that is higher or nth order linear differential equations with constant coefficients where the right hand side is 0. Thank you.